Assalamu alaikum. Welcome to W211. In the today's class, we shall continue our discussion on the circuits that contain the energy storage elements. But we shall, in this particular lecture, see the circuits that contains both the inductor and the capacitor, and hence these circuits are higher order circuits compared to the one we discussed in the last week. So let us start with our particular lecture. Our discussion shall be strictly on two simple structures. That is, we will first of all see the parallel connected RLC, and then we will study the series connected RLC. Now these parallel and the series connected RLC circuits, they will be tested in terms of the natural response. This will also be tested against the natural response, and afterwards we shall also look into the step response of these particular circuits. And in doing so, we will visualize the equations, the differential equations which are involved, and we will notice that these differential equations contains higher order derivatives compared to the first order circuit that we have discussed in the last week. Let us start with the parallel connected RLC circuit. So we have one capacitor, then we have an inductor, and then we have the resistance. So we have the voltage across this capacitor is V naught. I naught is the current flowing through this inductor L, and this is the resistance R, and here we have this VT. So in all the parallel connected networks, the goal is to find out this voltage VT. If you notice here that there are two energy storage elements connected in this particular circuit. So suppose that we have this circuit. This I naught is the current flowing through this inductance. Let us call this L. Let us call the current through this capacitor IC, and the current through this resistance IR. Now if we apply Kirchhoff's current law at this particular node, and we take all the currents away from this particular node, then we notice that IC plus IL plus IR, the sum should be equal to 0. Now using the basic expressions of these three elements, IC is equal to C dV by dt. This IL is 1 over L, 0 to T, V dt plus I naught plus V over R, and that is equal to 0. In here, if you see, this whole 1 over L integral 0 to T V dt plus this I naught, they constitutes the inductor model. Now because inductor requires the initial conditions, therefore we have included this I naught, and this I naught is actually the current which is flowing in this branch L before we have made this circuit disconnected from the source, because we are currently in a parallel connected RLC circuit and there is no source connected here. We are only interested in finding out the terminal voltages here, which is VT. Therefore this circuit is actually providing us the natural response of a parallel connected RLC circuit, right? So this I naught is the current which is flowing into this inductor prior to the disconnection of the source from this particular circuit. So the inductor model cannot be fully modeled or fully written unless and until we provide the value of the initial current which is flowing through it, and therefore we have included this I naught alongside the relation of the current for this particular inductor, and we call this a complete inductor model. So we have this inductor model. This is the relation of the capacitor for the capacitor current, because we know that IC is equal to C dV by dt, and this comes from the Ohm's law. We have applied the Kirchhoff's current law on this node by considering that all the currents are leaving the node, and thereafter we have written the simple expressions here. So let us move forward to find out the expression for this VT using this equation as a base equation. So let me call this as equation number 1, Now if I differentiate it with respect to time, we get 1 over r dv by dt plus v over l plus c d square by t by d square v over dt square, and that is equal to 0. Let me call this equation number 2. Now if you notice here that we have this d square dt over dt square, which is a derivative of order 2. So we have an order 2 derivative, and hence we call these circuits the second order circuits. So one very litmus paper test of going through the mathematical treatment of any circuit is, if any circuit contains both kind of energy storage elements in it, it is surely a second order circuit, and the treatment of first order circuit cannot be applied on that circuit. So we need to find out new ways to get the solution of these circuits that contains both the inductors and the capacitances in it. So this is actually a second order differential equation, and we have to solve it to find out the value of this Vt. So let us move forward. Let me call this equation number 2. We have started with this equation, which is equation number 1, and we have reached this particular equation number 2. Let us divide both sides by c. Dividing both sides by c, this becomes 1 over rc dv by dt plus v over lc plus d square v over dt square, that is equal to 0, and this is my equation number 3. Now this equation number 3 is actually an ordinary second order differential equation, and it has constant coefficients. How can we actually get the solution of this particular equation? Notice that this equation cannot be solved in the way we tackled the problem of the first order differential equation. For this, we need to assume some solution based on some sane assumptions. What could be those sane assumptions? For example, I can say that the the solution of this equation number 3 may be v is equal to a e raised to the power st. Now one can say why we have actually opted for this particular assumption. So there are various answers to this. One of the very logical answer is that we have seen in the first order differential equations that the solution of those equations contains the exponential part in it. Therefore it is quite possible that the equations containing higher number of derivatives also have this exponential part there. But in this particular equation, we need to actually elaborate, and we need to see if this particular solution is true for all values of time. Putting the value of v here also satisfies this equation number 3. So we need to see this particular aspect. So we know that in this particular equation, let us call this equation number 4, we have a and s. They both are unknown variables, and we need to find them as well. Moreover, we are more conscious towards establishing that this equation number 4 is actually a solution to this equation number 3. If I put v is equal to e raised to the power a e raised to the power s of t in all these equations here, we have this equation, we have this particular equation, then by using 4 into 3, we get a s square e raised to the power st plus a s e raised to the power st divided by rc plus a e raised to the power st divided by lc, and that is equal to 0. So this becomes my equation number 5. Equation number 5 can be rewritten as a e raised to the power st to s square plus s plus 1 over LC, sorry, S over RC plus 1 over LC, and that is equal to 0, and this is my equation number 6, right? Now there are two possibilities. If this equation is true, then either we have this part equal to 0 or we have this part equal to 0. Now let us examine this particular thing. If we have A equal to 0, this implies that the voltage is 0 at all time. So at all time we have no voltage in this given circuit. In this given circuit we have no voltage here. If A is equal to 0, this means there is no voltage that exists in any any branch of this given circuit. But we should notice here that there are two energy storage elements here. This is C, which is the capacitor, and we have this inductance L. They both have some energy which is stored prior to the disconnection of the source from this particular circuit, and that stored energy will be delivered to the rest of the circuit, and therefore it is not possible to assume that there is no voltage for all the values of time in this given circuit. And therefore, going with this approach, A cannot be equal to 0, right? So this is gone. The second thing is that this e raised to the power st, the time when it approaches infinity, this becomes equal to 0. But prior to that, for the finite values of time, e raised to the power s of t is also not equal to 0 for finite values of time. Then how this particular equation become equal to 0? This lies on the terms which are inside this parenthesis, that is s square plus s over rc plus 1 over lc. Now this term should be equal to 0 in order to satisfy this particular differential equation. Now if you notice here, this s square plus s over rc, so we say that s square plus s over rc plus 1 over lc, that is equal to 0. This is the characteristic equation of a differential equation and the roots of this particular equation determines the value of the voltage Vt. So we need to now solve this particular equation, and let me call this as equation number, this is equation number 7. If we solve for this particular equation, then there are two possibilities, s1 or s2, and that is equal to minus b plus minus under root b square minus 4ac divided by 2a. This means that the roots in this equation number 7 shall have two different values, one which is s1 and the second one which is s2. So based on this particular expression, equation number 8, if I substitute equation number 7 into equation number 8, then I get s1 s2 is equal to 1 over rc minus 1 over rc plus minus 1 over rc square minus 4 1 into 1 over lc divided by 2. And this can be written as s1 is equal to minus 1 over 2 rc into root of plus into root of 1 over 2 rc whole square minus 1 over lc. And on the same basis, s2 is equal to minus 1 over 2 rc minus 1 over 2 rc whole square minus 1 over lc. So these are my two roots that emerge from after we solve the equation number 7. So let me say that this s1 is my equation number, this is my equation number 9, this is my equation number 10, and this one is my equation number 11. To make it more clear, let me create a box here so that everything is isolated from the above equation. So now with that we have reached this equation number 9 and 10. We have got these two values S1 and S2. Now because we say that there are two possibilities for the roots which are in equation number 7, therefore there are two equations, there are two possibilities of this particular solution, and both the possibilities actually provide us the solution. So we say that their sum is also a solution. So let us say the equation number 6. Now this particular equation, it has two roots. So a e to the power st, equation number 6 becomes v is equal to a1 e to the power s1t plus a2 e to the power s2t, and this is also a solution. So what I mean to say here is that v is equal to v1 plus v2, because there are two roots that exist in this given network, and each root can be expressed in terms of, just a minute, let me rewrite this one. V is equal to v1 plus v2, that is equal to a1 e to the power s1t plus a2 e to the power s2t. Now let us say, now if this is true, then if I take the derivative of this particular term, let us say I want to take the derivative dv over dt, then this becomes a1 s1 e to the power s1t, and this becomes a2 s2 e to the power s2t. And if I take the double derivative here, d square v over dt square, then that is equal to a1 s1 square e to the power s1t plus a2 s2 square e to the power s2t. Now using this, now just move back to the original differential equation that we have solved, which was this particular equation, which is this particular equation, equation number 3, this one. Let us substitute the value of dv over dt and d square v over dt square with these two terms. So if I substitute, let us say this is a and this is b. If we substitute a and b into equation number 3, then we get a and b into equation number 3, then we get let me write the equation number 3 first. Plus 1 over RC dv by dt plus 1 over LC, v over LC, that is equal to 0. This was equation number 3. Let me write it again. Also we should notice here that a1 e to the power s1t plus a2 e to the power s2t, and this comes from this equation number 12. So this is our equation number C here. So now if I put these three equations A, B and C, if we put A, B and C into equation number 3, which is reproduced above here, then we have a1 e to the power s1t into s1 square plus 1 over rc s1 plus 1 over lc plus a2 e to the power s2t into s2 square plus 1 over rc into s2 plus 1 over lc, and that is equal to 0. And from this, these two terms are equal to 0. These two terms are equal to 0 because we have earlier discussed that this cannot be a solution, and therefore v is equal to e1 e to the power s1 of t plus a2 e to the power s2 of t. So it is shown that not only v1 and v2 are a solution, but their sum is also a solution. So v1, v2 and their sum provides solution to find Vt. So let us move back to this particular equation. We were here that a1 e to the power s1t plus a2 e to the power s2t provides us the solution of the voltage across the terminals of a parallel connected RLC branch in case of a natural response. So we can say we can revert back to start from that particular equation. This was equation number 12. So we have seen here that there are certain unknown quantities here. We do not know what is the value of a1. We do not know what is the value of a2. a1 and a2, these are two unknown quantities. Also, we do not know what is this s1 and what is this s2. So to find out these four unknowns which are present in this equation number 12, constants a1 and a2 are determined by the initial conditions of the energy storage elements. So we need to find out the initial voltage across the capacitor and the initial current flowing through the inductor. So these a1 and a2 can be calculated using the initial conditions of the capacitor and inductor. And here comes the necessary knowledge that is required to undertake the second order circuits. So about this s1 and s2, the values of the components, that is R, L and C values, determine these roots, right? Let us move back to this particular equation, equation number 10 and equation number 11. Based on these two things, or based on this equation number 9, which is a general form of these equation number 10 and 11, we can actually assign some special characters to simplify our knowledge in this second order circuit. So equation number 9 can be written as equation number 9 can be written as s1 comma s2 is equal to minus alpha plus minus alpha square minus omega naught square, right? And this particular equation is widely adopted in literature to find out the roots of the characteristic equation. What is this alpha and what is this omega naught? Here we have alpha equals to 1 over 2 RC, and this omega naught is equal to 1 over under root LC, right? So 1 over 2 RC is the alpha and omega naught is 1 over under root LC. Now we need to find out what is the dimensions of, or what are the units of these alpha and omega naught. Notice that this S1 and S2 is used with an exponential term, S1 e raised over S1 of t. So we need some dimension for these variables that gives us something which is opposite to that of time, right? Or which is the reciprocal of time. Or in other words, all these roots S1 and S2 must have the units in frequencies. Therefore, this S1 of t is some complex frequency that will cancel out with this time, so that we have a dimensionless quantity above the as a power of this exponential e. Therefore, this alpha in this omega naught must have the units of the frequency. Notice here that this alpha is popularly known as the Napier frequency, and this omega naught is known as the resonant frequency. And both of them have a unit of radian per second. And here we have this S1 and S2. These are known as the complex frequency, and it also has a unit of radian per second, because the equation on the other side has an equation which has a unit of radian per second. So now that we have established that this should have some units that makes this exponential term a dimensionless term, therefore all these are characterized in terms of the frequencies. This is known as the Napier frequency, which is 1 over 2 RC, and this one is known as the resonant frequency, which is 1 over under root LC. Let us say this is equation number 13. This is and let me write these in a little bit neat form, that alpha is equal to 1 over 2 RC and omega naught is equal to 1 over under root LC. Let us say this is equation number 14 and this is my equation number 15. Now if you notice here, S1, S2, and we have two frequencies in it, which is the neighbor frequency and the resonant frequency. So here comes the concept of that there are three possibilities that exist in this equation number 13. In this equation number 13, if you see, this S1 and S2 are dependent on this alpha and this omega naught, right? And this alpha and omega naught are dependent on the values of the components which are connected in that parallel connected RLC circuit. This means that there are three possibilities that may exist. The number one is that this alpha is greater than this omega naught, right? The other one is that this alpha or the neighbor frequency less than the resonant frequency. And the third possibility is that the neighbor frequency is equal to the resonant frequency of a given circuit. So here comes the three different case scenarios that now we need to address before we finally reach the solution of this circuit. Let me write down the three possibilities here. So the possibility number one is that omega naught square is less than alpha square, right? In this case, we have both the roots will be real and distinct, and the response is called an overdamped response. The second possibility is that this omega naught square is greater than this alpha square. In that particular case, both the roots S1 and S2 will be complex and conjugate, and the response of the circuit is known as an underdamped response. And the third option is, or the third possibility that exists here is that omega naught square is equal to alpha square. In this case, both roots will be real and of course equal. So this is called the critically damped response. So we shall see that based on the values of the R, L, and C, the circuit voltage at the output terminals in case of a parallel connected or in case of a series connected circuit, in any second order circuit, we can have the three responses. The first one is this overdamped response. We may have an underdamped response, or we may have a critically damped response. So let us find out these three responses, and let us see where we will end up with the solution of this second order differential equation. So let us first of all see procedure of finding the overdamped response. So let me write that as procedure for overdamped response. So the procedure for overdamped response is quite simple. The first step is that we shall find out or calculate the roots of the characteristic equation, that is S1 and S2, using the values of R, L, and C. After we have calculated the roots, we can establish whether it is an underdamped response, overdamped response, or a critically damped response. But considering for this overdamped response, the next move is to find out the initial condition of a given circuit, and for that we required V0 positive and dV0 positive over dt, V0 positive and dV0 positive over dt. How can we find out this V0? That is by using the initial conditions. That is by using the initial conditions. So what is this V0 plus? V0 plus is the initial voltage which is stored in the capacitor, right? And what is this dV0 positive over dt? This is the rate of change of the voltage right after the switching at time t equal to 0. How can we find this thing? For example, we have a given circuit here. We have this inductance here and we have this resistance here. So at t equal to 0, we disconnected this switch, right? So this is where we want to find out the Vt. We do know that there is some inductor current available because that was flowing here. Inductor was short circuited and therefore all the current was flowing through the inductor. So right at time t equal to 0 positive, what shall happen? The inductor current cannot change instantaneously. However, it has a tendency to change instantaneously in these two branches IR and this IC. So now if we know what is the current I naught which was flowing in this particular inductance, and we do know what is the voltage V here that this capacitor will try to maintain, then we do know what is the voltage across this resistance as well. So based on that, we can find out what is the current IR which is flowing in this resistive branch. Now if I apply the Kirchhoff's current law at that particular node, then IC is equal to I naught minus IR. And based on that, I can get what is the value of this IC. Because you should never forget this thing, that the current through a capacitor can change instantaneously. Therefore, the current through this capacitor will change instantaneously. What will happen as a result? There is a current that shall start flowing through this capacitor right after time t equal to 0. That is t is equal to 0 positive. And therefore, the current shall be start moving through these capacitor plates. What is this IC? IC is equal to dV over dt. So what is IC 0 positive? That will be equal to dV 0 positive over dt, and that is equal to with this sign C. So the value of this dV 0 positive over dt is equal to IC 0 positive divided by the value of the capacitance C. Notice here that this capacitance C is known. This IC 0 positive is calculated by using this Kirchhoff's current law at this particular node, and therefore we get the value of dV 0 positive over dt. What about this V0 positive? This V0 positive is equal to V0 negative, and that is equal to Vc before we turn on the switch at t equal to 0. So therefore all the things they are well connected with each other, and the right application of the circuit analysis technique that we have studied in the previous lectures is essential in solving such type of circuits that contain both the energy storage elements, which are the inductance and the capacitance. So as the second step, we will only try to find out the value of this V0 plus and dV0 plus over dt, and that requires a careful understanding of the circuit techniques. Whatever we have learned so far, those techniques are vital in understanding what is happening in this particular circuit. So as a third step, we will find out the values of A1 and A2, right? And what is the value of that A1? That V0 plus is equal to A1 plus A2, right? What is this V0 plus? This V0 plus is right at a time instant t equal to 0. It is a very small quantity just after we have made the switch operated at time t equal to 0. This means that this V, which was equal to A1 e raised to the power S1t plus A2 e raised to the power S2t, putting this t equal to 0 means that we are left with only A1 plus A2, and therefore this is shown here that V0 positive is equal to A1 plus A2. Also notice here that we have dV0 positive over dt, which is equal to IC 0 positive over C, that is equal to S1 A1 plus S2 A2, because the derivative of this particular term we have earlier seen here, that the derivative here, let me show you this particular equation here, this one. So this is at time, right after a time dV0 positive over dt. we will get rid of this exponential term and we will left only with a1 s1 and a2 s2. So this gives us the hope to find out the solution in case of an overdamped response. So the initial conditions are calculated. Let me revise this thing again. Based on any given circuit, we first need to find out what is the characteristic equation, as what is the roots of the characteristic equation, which are s1 and s2. Once we calculated the value of s1 and s2, we then go with the using the initial conditions, we find out this dv 0 positive over dt and v naught plus, and after that we tackle the unknown variables a1 and a2, and thereafter our equation is fully solved, and then we can actually know what is the value of the current and the voltages through different branches at any given instant of time. So let us solve one example if we have understood this correctly. So this is example number 8.1 from your reference book by Nilsson. So we have, let me draw the circuit here. We want to find out these voltage Vt. The capacitor is, this is 0.2 microfarad. The inductance is 50 millihenry, and the resistance is equal to 200 ohm. So we have current I naught here. We have the voltage V naught here. Also we have the three branch currents. This is IC, this is IL, this is IR. Now as a first step in this particular circuit, we shall first see if this, we shall first calculate the roots, and we will establish if the circuit is critically damped, overdamped or underdamped. To do that, let us first of all find out what is the value of alpha. So alpha is equal to 1 over 2 RC, that is equal to 1 over 2 into 200 into C, which is 0.2 microfarad, and that is equal to 1.25 into 10 to the power 4 radian per second. About this omega naught, that is equal to omega naught square is equal to 1 over LC, and that is equal to 10 raised to the power 8 radian square over second square. Because this omega naught square is less than this alpha square, therefore this is the response is overdamped. If it is required to find out the value of the circuit parameters to create a critically damped response, then we need to actually equate alpha square equal to omega naught square, and using the value of alpha, which is 1 over 2 RC, that should be equal to 1 over LC, and from that we vary the value of this resistance R to create a critically damped response. So if for this given circuit we want to create a critically damped response, then keeping the values of L and C like they are given in this particular circuit, the value of R can be notified as 250 ohm for a critically damped response, right? For a critically damped response. So this is how we actually solve simple circuits. First of all, finding the roots. The second important point is how to find out the root S1 and S2. S1 and S2 can be calculated by using equation number 13 above. So if you notice here that we have this equation putting the values of alpha and omega naught square in this particular equation will give us the value of the roots which are available. So you see, we have said that the roots will be real and distinct. So the value of S1 is equal to minus 5000 radian per second, and the value of S2 is equal to minus 20,000 radian per second. So we have we have solved this equation number, this particular example number 1. Now using the same circuit that is shown here, it is further required to find out the initial current in each branch of this given circuit with some initial values given. So what are the initial values which is given? Now that in example number 8.2, let us move on to example number 8.2 with the same circuit. We have this V naught, this is C, this is I naught, this is L, and this is R. We want to find out what is this VT here. Now the initial conditions provided here is that V naught is equal to V naught 0 negative is equal to 12 volt. These are the initial conditions. The second initial condition is IL, let us say this is IL 0 negative, also let me say this is VC, IL 0 negative is equal to 30 milliampere, and we want to find out the initial currents through all the three branches in this given circuit: the R, the inductance L, and this capacitor C. Also we need to find out the dV over dt, which is the initial voltage right after the switching, and the expression for this output voltage Vt. And thereafter we want to sketch the voltage Vt. So let us start with this particular numerical. Now that R is equal to 200 ohm, inductance is equal to 50 millihenry, and this capacitance is 0.2 microfarad. These initial conditions are very important to start with the solution of this particular numerical. So using these two equations, using these essential initial conditions, we know that IL 0 negative is equal to IL 0 positive, and that is equal to minus 30 milliampere. The second important point here is that VC 0 negative is equal to VC 0 positive, and that is equal to 12 volt, right? So what is the current? Based on these two things, we can find out what is the current flowing in this resistance R. So the current in R is equal to V over R, and that is equal to 12 divided by 200, and that is equal to 60 milliampere. Now we have to apply the KCL here. Let us say this is node A. So applying the KCL at node A will provide me the current which is flowing through this capacitor C. So the inductor current minus the current which is flowing through the resistance give us the value of the capacitor current. So IC 0 positive is equal to the current was that is equal to, sorry, this is not minus 30, this is this is 30 milliampere. Just a correction here, this is not minus, this is 30 milliampere. So IC 0 negative is equal to minus IR 0 positive minus IL 0 positive, and that is equal to 60 milliampere plus 30 milliampere with a negative sign here, and this gives me minus 90 milliampere, and this is the current IC 0 positive. Now because I have known what is the value of IC 0 positive, I can find out what is the dV 0 positive over dt, and that is equal to IC 0 positive divided by the capacitance value C. So using this expression, which is actually the expression for the current through a capacitor, I can find out this to be equal to minus 450 kilovolt per second. So now that we have solved most of the equations, we can now find out the value of this R, L, and C. We have earlier calculated the values of these alpha and this omega naught as well. So alpha was equal to 12,500, while this omega naught square was equal to 10 to the power 8. So we will use these. We will plug these values in this equation as well. So S1 is equal to minus 5k, and S2 is equal to minus 20k, and this is the same as that of the previous equation, as that of this previous numerical, where we have calculated the roots of the same circuit, which is this one. So now we'll revert back to the general solution of an overdamped response, and that overdamped response is given in equation number 12. So this is the equation number 12. Let me show you this equation. This is my equation number 12, and here I have to put in all the values. S1 is known, S2 is known, only that A1 and A2 are unknown. That we shall find out. We shall find out by using these two equations, right? So let me write down the equation. Now equation is V is equal to A1 e to the power S1t plus A2 e to the power S2t. What about this A1? A1 is equal to I have written it here. A1 plus A2 is equal to V0 positive. So A1 plus A2 is equal to V0 positive. Also we have, for the second one, this IC0 positive over C is equal to S1 A1 plus S2 A2. So I will write this as well here, that we have IC0 positive over C is equal to S1 A1 plus S2 A2. And based on these two equations, this V0 plus is unknown, so that is equal to 12 volt. S1 is known, S2 is known. Also this particular side, this whole thing is equal to minus 450. So we have two unknowns, and there are two equations. So these two are solvable, and if I solve this particular equation, then I get A1 to be equal to minus 14 and A2 is equal to 26 volt. So the solution here is that the voltage for this particular circuit Vt is equal to minus 14 e to the power minus 5 kt, right, or 5000 t. Let me write it as e to the power minus 5000 t plus 26 e to the power minus 20,000 t. So we need to now see if this solution is true. This is the first thing after we have solved this equation. So if you notice here, putting t equal to 0, V0 becomes equal to 12 volt, and this is exactly what was given as V0 negative, which was our initial condition. So this equation is exactly true for us. And also solve this particular equation, then dV0 positive over dt is equal to minus 440,000 volt over second. Now to plot this particular numerical, we usually use the simulation softwares, because such functions are complex and therefore it is not feasible to plot them on paper. However, this response, if this is 12 volt, this shall be something like this for 250 microsecond time. This is the time, this is the voltage, and this is something equal to minus 5 volt. So this is how we solve for the response of a circuit which is overdamped. Now in the next class we shall solve for the solution of the underdamped response. Till then, practice all the questions that are given in your reference books and in your textbooks, specifically containing the circuits for finding the roots of the characteristic equation and finding their response using the values of the R, L, and C. Till then, take care. Allah Hafiz.